All right, welcome to a Sunday afternoon video. Things are going really good for me today. Having a really good day. It's good weather outside and everything. So let's continue to work on this exam. The last video, we finished up the advertising IPv6 routes over IPv4 transit. So now we're going to work on advertising IPv4 routes over IPv6 transit. So let's read the overview. In an IPv6 network, BGP typically advertises IPv6 network layer reachability information over an IPv6 session between BGP peers. In earlier releases, Junos OS supported the exchange of INET6 unicast, INET6 multicast, or INET6 labeled unicast address families only. This feature allows the exchange of all BGP address families. In a dual stack environment that has IPv6 in its core, this feature enables BGP to advertise IPv4 unicast reachability with IPv4 next hop over an IPv6 BGP session. This feature is for BGP IPv6 sessions only, where IPv4 is configured at both endpoints. The local IPv4 address can be a loopback address or any IPv4 address for an IBGP or multiple hop eBGP session. For single hop external BGP speakers that are not part of BGP confederations, if the configured local IPv4 address is not directly connected, the BGP session is closed and remains idle and an error is generated, which is displayed in the output of the show BGP neighbor command. To enable IPv4 route advertising over IPv6 session, include the local IPv4 address as follows. Note, you cannot configure this feature for INET6 unicast, INET6 multicast, or INET6 labeled unicast address families because BGP already has the capability to advertise these address families over an IPv6 BGP session. The configured local IPv4 address is used only when BGP advertises routes with self next hop. Well, that's usually next hop self is usually how that's, so that really tripped me up there. When IBGP advertises routes learned from eBGP peers, or the route reflector advertises BGP routes to its clients, BGP does not change the route next hop, ignores the configured local IPv4 address, and uses the original IPv4 next hop. All right, so here's our example. This example shows you how to advertise IPv4 routes over IPv6 BGP session. In a dual stack environment that has IPv6 on its core, there is a need to reach remote IPv4 hosts. Therefore, BGP advertises IPv4 routes with IPv4 next hops to BGP peers over BGP sessions using IPv6 source and destination addresses. This feature enables BGP to advertise IPv4 unicast reachability with IPv4 next hop over IPv6 BGP sessions. Okay, so we've got the same kind of topology, thankfully. So here's the overview. Beginning with release 16.1, Junos OS allows BGP to advertise IPv4 unicast reachability with IPv4 next hop over an IPv6 BGP session. In earlier Junos OS releases, BGP could advertise only INET6 unicast, INET6 multicast, and INET6 labeled unicast address families over IPv6 BGP sessions. This feature allows the BGP I think this is the same thing that was written up here. So I'm just going to skip this. Let's just get right to the configuring. A lot of this is kind of unnecessary to read. So it looks like we've got the same topology with router 1, router 2, and router 3. It's just we're going to be breaking down the BGP connections that are set up with IPv4 neighbors. So you can see that right here on router 2, we've got the neighbor address is an IPv4 address, and we're going to be resetting it up, but with IPv6 neighbors. And in addition to that, all of these routes that we're adding in, I forget where we're doing that. We're doing it on router, let's see here. So we've got some static routes that we're advertising into BGP. I remember, I just don't see where those have been advertised. So yeah, I don't see any static routes. Here we go. So it's kind of, oh yeah. So we were advertising both a IPv4, kind of nothing special, but the thing we wanted to show was that you can advertise a IPv6 route, even though your BGP session is to a IPv4 address. But now we're going to show that the opposite is also true. You can advertise a IPv4 route, even though you have set up a BGP peer to an IPv6 address. So let's get started. And I'm sure there's a lot of overlapping config. Well, actually, there's probably not going to be because we're changing a lot of things. So just going to roll back everything. All right. Perfect. Make sure everything is good to go. And it is. Yeah, so unfortunately, this is just for the most part, a config video. It's not going to be all that entertaining. Apologize for that. You can see we're doing that same setup. Oh, well, actually, it looks like we are using a kind of a different addressing convention that we were using in the last one, because the last one we took the IPv4 address and we just put it at the end of the IPv6 address, but we included 3 Fs, F, 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 F in the middle for some reason. I don't know why, but we're not doing that here. So whatever reason it was for the other one, that's not going to be necessary for advertising IPv4 over IPv6. Though it might be advertised, it might be necessary for advertising IPv6 over IPv4. I'm not too sure about that. I'm really not going to worry about it that much because I don't think it will be important to know for the test. I think EUI64 will be important, but not that random all Fs thing. Well, I'm gonna actually look at that quick. So IPv6, FFFF, IPv4. Oh, okay. So this is actually kind of a big thing. So Let's see what the wiki has to say. It's usually not too bad. It can vary a lot. So here we go. So during the transition of the internet from IPv4 to IPv6, it is typical to operate in a mixed addressing environment. For such use cases, a special notation has been introduced, which expresses IPv4 mapped and IPv4 compatible IPv6 addresses by writing the least significant 32 bits of an address in the familiar IPv4 dot decimal notation, whereas the other 96 most significant bits are written in IPv6 format. For example, the IPv4 mapped address, IPv6 address, :FFFF, :C000, :0280 is written as FFFF 192.0.2.128, thus expressing clearly the original IPv4 address that was mapped to IPv6. Okay, so it doesn't say anything specifically about those 4 Fs. I kind of was hoping it would, what the significance of those are, and if that's part of the mechanism that expresses clearly the original IPv4 address and the fact that it was mapped. It's not clear if those 4 Fs are a part of that. So I'm gonna have to look for another resource, but luckily I've already got one found with a tab open for it. Ah, here we go, perfect. So IPv6 will have to be phased in gradually because up until this point, the majority of IP protocol addresses through internet history have been IPv4. So internet engineers designed IPv6 in a way so that it could coexist with the current internet framework and coexist with IPv4 over a long-term transition. IPv6 provides a way to accommodate IPv4 addresses within its address space. One technique used is called IPv4-mapped IPv6 addresses. That hybrid address consists of 80 0 bits followed by 16 1 bits, FFFF in hexadecimal, followed by the original 32-bit IPv4 address. Too technical for most of us. Okay, so this one, they mentioned that. So sure enough, this one did mention the 96 bits. I kind of want to go back and see what it had to say about that. So it says, whereas the other are written in IPv. Well, yeah, I don't know what that means. Wikipedia kind of failed me on this one. I really like the this one here, and it looks like it's kind of to a more general, lower level audience, which sometimes can be helpful even if you are at that high level. So we can see that any IPv4 mapped IPv6 address is going to be signaled as such by 80 0 bits followed by 16 1 bits. So you're just going to have the IPv4 address, but you're going to have : :FFFF : and then the IP address in hexadecimal. So here's an example of how that would work. IPv4 address 169.291.13.133 maps to IPv6 address 00, so all zeros, FFFF, A9DB 0D85. Simplified using the abbreviation rules of IPv6. The prefix of the mapped address places it in the range of mapped IPv4 addresses. Because of that, the IPv4 portion is often left in the more familiar dotted decimal format. Okay, so this is something we're gonna be looking out for during all of this. And I kind of wish I hadn't gotten rid of my configuration. I can always roll it back. In fact, let's do that. Let's roll back. So do rollback 0. Oops, top, rollback 0, rollback 1. Aha, okay, so yeah, it looks like we're not going to have to do that rollback because we're going to see this quite a bit in this exercise. So let's just keep working through this exercise and have in our minds the mechanism for IPv4 mapped IPv6 addresses that can be special, because you wouldn't think, if you were just looking, hopefully to someone who's an expert, and hopefully to me as I'm taking the exam and in production, I would see something like this and immediately think, well, that's funny. These are not colons, these are dots. How does that work? Well, it works because it's a IPv4 mapped IPv6 address. So you can have this special formatting here, but it's only valid if you have : FFFF. So that's something that I am really glad I went in and learned more about. But continuing on. Come on, there we go. So I wonder if my commit's going to be rejected for this one then, because we can see we're using the special dotted format, but we're using 2 colons. So if this were a true IPv6 address, this is not a valid format. It's got to all be in hexadecimal, and it has to have only colons in it, no dots. But if we give it the special signifier saying that it's a IPv4 mapped to IPv6 address, we can have this hybrid notation with dots and colons, but only if we signal using the least significant or using the most significant first 96 bits, with the first 80 being all zeros and the next 16 being all ones. Then it knows it can accept this special syntax. So this is definitely something that if it turns out that I can't commit this, I will be submitting, well, first I will be testing to see if this works with the all Fs in the 81st through the 96th bit. And if that works, I'll be submitting a downvote saying that the prefix that signifies that you're using IPv4 mapped to IPv6 addresses is : FFFF, not : and I'll request that they update their documentation. So you can see just how much I learned about this subject just by kind of having that question and not allowing myself to kind of just move on and let it go and going in and diving deeper. So I've been keeping a list of the running themes of this channel, and this is definitely one that I don't have on here, and it's definitely a big running theme, and it's about curiosity. For now, I will just go curiosity, but it's going to be a lot more kind of nuanced than just curiosity, because as I've mentioned, and this is a big running theme in this channel, I hope, is curiosity really isn't enough. I mean, and curiosity can be dangerous in some cases. So it's really, the word curiosity is kind of not enough to fully explain the running theme of this channel that I intend. But I think for now, it's kind of a good enough placeholder, and I'll hopefully elaborate on that at a later time. And here's the special discard knob where it will send So, so yeah, here's the knob we used before was reject. So with reject, it will drop packets, hey, we're just using this for whatever reason, traffic's not actually meant to go here. So if somebody sends traffic there, we say, hey, what are you doing? Like, here's your ICMP unreachables. There's nothing to see here. This is a dead end. But another thing you can do is use the keyword discard, and you do the same thing, except for instead of saying, what are you doing? There's nothing here. You just don't say anything at all, and you just don't respond back, and then it times out on their end. So that's kind of if you're being attacked by a botnet, or you're worried about distributed denial of service attacks, I think this would be an important consideration, because you don't want your devices responding back in with large amounts of ICMP traffic just because somebody requested something. So I think in general, discard, if you're concerned about DDoS, would be a better option than reject. But of course, if you're concerned about network clarity and you want to bring some perhaps Pythonic principles to your network, Pythonic principles being readability and kind of the acknowledgement of people working on your things, and kind of treating those people as such, and kind of making their lives easier. In that case, yeah, that reject knob can tell them in more explicit terms what is happening, which can be very useful. Yeah, I was actually setting up a VPN for this lab, and I kept getting the message destination host unreachable from my server. And that was enough information for me to figure out how to overcome the issue I had, which was I had configured the wrong IP. So yeah, it's important to kind of give clues and let your administrators and people working on your network get their jobs done fast and conveniently. But of course, we all know security is a trade-off between convenience and security. So if you disable that discard, you can have more security because your device won't be responding back. It'll just be throwing that traffic away. So you won't be allowing people to ask something of your device unless what you can deliver to them is something that is necessary for them to receive. Oops. Okay, so here's that moment of truth where we can see if you can use this mixture of dotted decimal notation with this IPv6 hexadecimal colon notation without having the first portion be all zeros and then 16 bits of all ones. So let's see if that works. Aha, so here we go. Oh, never mind. It looks like there's, I set the autonomous system to be the same as the neighbor. And I said that's external. So this is a really good lesson actually, because we can see external peers AS 64496 must not be in the same as the local AS 64496. So I set the local AS here. So now if I go into edit protocols BGP, show pipe display, set relative, I set the peer AS to the same as the local AS. Well, what if it's an IBGP connection? You know, it should just know that. I told it explicitly to be an EBGP connection, so they have to be different. I'm pretty sure, I know, like, I think in Cisco and stuff, you can just have it implicitly. It's smart enough to know whether it's internal or external, depending on whether the peer AS you configure for it is the same or different as your local AS. That's something you might be wondering about, is why do I need to specify whether it's external or not, if it can just, you know, see and prevent me from committing. So it knows what the ASs are, it knows whether they match or not. So why do I need to give it that extra keyword? And the answer to that is I don't think you do, but again, if you're into kind of Pythonic principles, like if you're familiar with the programming language Python, explicit is better than implicit. So it just says right there, it's an external connection. You don't have to go look up what the local AS is to know. So kind of having your naming and your commands tell you what's going on is something I would always advocate for, just having things as clear as possible. And of course, you know, if there's a unwanted, like a hacker or someone breaking into your gear, they're gonna have a better time if you do that, which is no good. But I think that's not as likely as a scenario as somebody intending to do good on the network, working on it, making a mistake because your configuration was just a complete mess. That's more likely to harm your network than an attacker using clear information against you. All right, so yeah, it looks like it accepted this without the 4Fs. So that's kind of interesting. I wasn't expecting that. Looks like I don't have to submit a downvote, but I'm very surprised that it did not require those 4Fs, because it said in here that it did. So I wish I could submit a downvote here, but I'll just move on to router 2. Okay, so here's the policy where we're going to change the next hop, and it's going to be next hop self. So we're not going to be setting a local address. And that makes sense because there's probably some difficulties in setting the local address if you want to use both IPv4 and IPv6 addresses. So family inet unicast local IPv4. Ah, okay, never mind. We are actually setting the local address, but we're setting it to an IPv4 address, even though the neighbor is an IPv6 address. So that's interesting. I'm glad I caught that. Oops, I gotta enter that in. Perfect. Time for Ebgp, type external. The peer AS different than the one that is on here. But same idea with a IPv6 neighborship. But with an IPv4 local address. So here's the good old next hop self, but let's make sure to, in the Wireshark capture, take a look at what that actually means. Is that going to mean that the next hop is this address? Is it going to mean that it's the loopback address? What does this term self mean? And let's actually look at the, aha, here we go, perfect. So we already know. Use a local address as the next hop address. So here we set the local address. It's going to be a local IPv4 address. So even though it's sent over an IPv6 neighborship, the address is going, the next hop is going to be sent with IPv4. So of course that's going to be problems if you're advertising IPv6 routes, but the purpose of this is IPv4 routes over an IPv6 connection. So that, one thing I forgot, and I'm going to actually roll back these changes, is I wanted to have a Wireshark capture going between router 1 and router 2 to see what's on that link and what happens when I commit this. It's definitely going to be a big part of understanding what is going on, so I definitely don't want to skip that. And this, of course, ties back into the running theme of the channel. It's, you know, for right now, the placeholder word for it is curiosity, but I guess dive deeper is a good one. Extra mile, you know, that sort of thing. I'm sure I'll come up with a better explanation of it, but it's kind of the opposite of look before you leap. But cautious curiosity is kind of taking both into account. So let's see here. Did it open? It did not open. So I'm probably going to get the GNS error now. Yep, it says it's already capturing, but it never opened the Wireshark. Let's just try to open Wireshark right now and see if it truly is capturing. Because just because it didn't open automatically doesn't mean I can't still open it. So, oh, it's probably because this update keeps making things difficult. So it looks like there's a lot of traffic on this link. So, oops. Yeah, so this is the, this is live. Yeah, this is my home network, so I don't want to sniff that. This is just my local area network. It's not like my public traffic. It's just, and you can see like let's find the so let's say, yeah, let's find this juniper.net documentation. So we're going to go to CMD and we're going to do NS lookup. Whoops. Let's see here. There we go. So now the DNS server I'm using says that it's IPv6, but it also says that it's at this IPv4 address. So let's do ip.address equals this. Oh, and that's interesting. We don't have any traffic. I mean, I didn't like refresh it or anything, so there might not be any new traffic. I mean, we can look at the traffic on my local area network. There's nothing kind of interesting. One thing that will be interesting is I have some automatic like lights, some smart lights, smart plugs. So we'll probably see those like reaching out every once in a while. There's probably like a TCP session or something. But yeah, I mean, there's interesting stuff. I'm not sure what LLMNR is. I think local multicast name resolution. So, I mean, that's the problem though with looking at just random Wireshark captures, is you're just going to see a lot of stuff that isn't really relevant. So especially when studying for a test, it's really not something that is going to be productive. All right, so let's just keep moving on. Let's do a restart of the GNS so that we can get the Wireshark capture working easier. And hopefully I won't lose any changes. All right, so now we can see it's telling us the truth. So let's stop it, start it again. And we were in the middle of capturing router 2, so let's go back onto there and get ready to do that commit. So show pipe compare, looks good. And of course, we're not going to have any traffic right now. It's just a dead link. There isn't even any IP addressing on there or anything. But now we should see all sorts of traffic. Hopefully, things are working. Let's see here, show BGP summary. Oh, it's an active state. So, okay, now we've got an open sent. Maybe we can get over to established. Yep, so we made it to established. So very clearly there's an issue with the Wireshark capture. It's not showing the traffic for some reason. But it did go into established, so it's not like I configured the wrong port or anything like that. And we can even look at the description some more and see, yep, 0 R1 to R2. So I did configure the port correctly. Let's see if there's now traffic. Aha, so there is traffic now. So let's try to figure out what that next hop address is going to be. Is it going to be IPv4 or is it going to be IPv6? So we're not going to see it in the keep alive messages. Okay, so I'll give you another 3, 2, 1 countdown, and the question for you to ponder is what kinds of messages will we see the next hop in? 3, 2, 1. So they're going to be in the update messages that have the path attributes that are for a new route being introduced. We're also going to get update messages for routes being removed, but we're not going to see the next hop in those messages. There's no reason to include path attributes in a route that you're going to take away, only in a route you're going to add. Okay, so let's see if we can get it to do the thing I want it to do, and then go and look at that next hop. Configure private. Now I have a feeling, oh, I can just do clear BGP neighbor 4101. Okay, so now we got, yep, 4-way disconnect here. So now we're going to get a, oh, but you know, as I noticed in other ones, typically when I clear something or bounce a port or do, like, whenever there are a lot of fin packets, it seems like the Wireshark capture stops. So let's get it as fresh as it can possibly be, and then try clearing that again, and hopefully it will persist over that. Yeah, it's really buggy, but it's, I mean, one thing I can do as well is look at the monitor traffic instead of just the Wireshark capture, because monitor traffic will also be capturing, but it's not as, unfortunately, it's not as verbose as what we'll get from the Wireshark capture. But let's set that up. So monitor traffic, no resolve, interface 0. And let's include the layer 2 headers, and let's print the ASCII information. So now let's clear that off, and hopefully we'll see the fin packets, 4-way disconnect, but then we'll also see the reconnect. So let's make sure that we are reconnected before determining whether or not the capture has stopped. So we're getting lots of packets here now. Still in active state. So I think this side here is probably still established because that hold timer has not expired. That's going to take about 90 seconds. Okay, but now we've got our keep alives. So I'll stop the captures on GNS3 and on the device. And now let's look at those update messages and find the next hop. So this is one for just withdrawn routes. Okay, so here's the update message for, oh, I see. No, it's not the one for withdrawn routes. This is an update from .2, which doesn't have any routes to give. Only route 1 is going to be introducing new routes. So you get an update message on each side of the peering, but if there's no routes to update with, you'll just not get anything, but you'll still get that message. It's not like if that has nothing to say, it won't say anything at all. No, it'll only send you that update message. But if there's nothing for it to tell you, you'll just get a blank small one like this, 109 in length. But you'll get a bigger one if there is stuff to say. And it looks like it's mixed in with an empty one as well, which is kind of interesting. But here's the path attributes. So our well-known mandatory path attributes. Next hop, AS path, and next hop, AS path. Oh my God, and what else? I can't. Well, so we know that I think origin, next hop, origin, AS path. Does that sound right? Aha, yes, it is. So next hop, origin, AS path. Those are our three well-known attributes. And sure enough, we've got a IPv4 address as the next hop, even though we configured BGP in IPv6. And the reason we've got that is because the configuration of IPv6, show configuration protocols, BGP, pipe display set relative, includes this local address statement, but it specifies it as a local IPv4 address. So let's look through some of the packets that we sniffed here. Maybe we can get an update, something. Yeah, unfortunately, it looks like, so we do have BGP messages. You can see the port number is listed here. So they are BGP messages, but unfortunately, it kind of looks like it leaves a bit to be desired. We can't see the next hop. We can't see the path attributes. We can't even see whether it's a keep alive or an update message. You know, perhaps I wasn't using the appropriate filters, but you could see that just without learning more about how this works, it's not going to be sufficient on the exam. Maybe detail would work. Let's see here. I'll clear this off again and see if detail works. In the meantime, I can close this because we looked at that next hop. So be nice to know, aha, so yep, when I add detail, I get the type of BGP message it is. So I get my keep alives, and then since I cleared that, I'm gonna get a notification message. So this is actually perfect. This is like everything you would need to know anyways. So that's kind of the ticket is that detail keep knob at the end. So hopefully it'll come back up and we'll see our updates. Aha. Oh, this is really nice. Yeah, this is going to be great on the exam too. Like I think this will be, look at this. So here's our BGP update message. And we can see the next hop, the AS path, and the origin. Everything is really perfect, really nice and easy. Updated routes there, updated message. And then up here, yep, we've got more. This is, oh, here we got the open message. And the open message looks like it includes even easier to see details than in Wireshark. Subcode connection rejected. That's interesting. Not sure what that is. But yeah, so we can see just how valuable that TCP sniffer can be. I mean, I wish Cisco had something like that, but Juniper really is, I think, the king of really useful CLI management commands. Like I remember like in when I was in networking school, the teacher said like Cisco's like the king of like reliable hardware or something like that. So it's like as I was mentioning over, like there's trade-offs on things you can invest in, and I think Juniper went the way of good software on their gear, and Cisco went the way of good hardware. But Cisco iOS XR, iOS XE is starting to adapt those principles that have been kind of had their ground broken by Juniper, that Juniper developed initially. All right, so we've got one last router to go. All right, so hopefully this will commit without issue. Let's start a Wireshark capture on the link here so that we can see what happens when it comes up. Hopefully we'll see that collision, connection collision, because we did not use the passive keyword. I'm sure that applies to IPv6 connections as well. That's something I'm actually kind of curious about. I'm going to do edit protocols BGP group IPgp v6 and do show pipe display set relative. And let's see if we actually do have that for a neighbor that is an IPv6 address. So it's going to be set neighbor, and then we'll see if the passive keyword is there. So yep, there it is. We can prevent that connection collision and have open messages only sent from one peer and not by both, and compete for which one initiates the connection. All right, so let's, before committing it, also get some Wireshark capture, or sorry, some device CLI captures. So yeah, let's just do it on 0, 1, just each interface pointing to 0, 3. Oops. Oh, right, it's not up yet, so that's not gonna work. We can look at the other side, that might be interesting. Okay, so now let's hit commit. Aha, so here's a bunch of traffic coming in. What do we got? We got ARPs, we've got, I'm kind of surprised we've got ARPs actually, because, oh, no, it's not an ARP, it's not an ARP, it's a neighbor solicitation. So we'll go back and look at that because we don't have any ARPs in IPv6. We have neighbor solicitation messages, but they kind of serve the same purpose as ARP. They just won't be broadcast, which is a really nice feature because broadcast traffic can cause broadcast storms and can bring down your whole layer 2 segment. All right, so that seems to be enough traffic capturing. We can see on this side we don't have nearly the same kinds of traffic because this is pointing this way. So we're going to have things going out, but we're not. It's just going to serve as a transit router, so we're really not going to see anything interesting being processed at the router. Let's go back and look at that neighbor solicitation message. So who has, so that's very familiar, just like an ARP, but the source link address, but the address is not all Fs, it's not broadcast. It's I believe it is multicast, but I will check on that because that's probably going to be important for me to have right. So FF02 is what is significant. And yes, exactly, it's a multicast address. So instead of having a broadcasting address that can take down your whole layer 2 segment, if you have a broadcast storm, neighbor solicitation for IPv6 uses a multicast address. All right, so yep, and then we got some ICMP. We've got, here's where we got our open messages. Let's try to find our 3-way handshake. So we'll see a TCP SYN. Well, actually it depends on where it was initiated from. So let's look at this open message. And it was initiated from .2, which I'm not sure if this is .1 or .2. I think it's .2. Show int terse pipe match GE dash. So yeah, it is .2. So it initiated here. So this is going to have a SYN. It will receive a SYN ACK and it will reply with an ACK. So out will be the SYN. So what is this? This looks like a SAC. Is that a SYNAC? I'm not sure. Yeah, I'm not sure where the three-way handshake is, and I'm not sure if we'll see the whole thing or we'll just see one side of it. But you can see this is TCP BGP traffic. Yeah, I kind of was hoping that it would show up. It's still going to have a three-way handshake. It's just going to be for a IPv6 address. Well, maybe it'll show up in the Wireshark capture. Oh, Wireshark capture stopped, of course, because of that bug. So I guess it's not important to find. Well, why don't I just refresh that neighbor? So clear BGP neighbors all, and then we'll see that SYN-SYNAC ACK. I think we saw it before, but I'll just drive home the point that whether you're using IPv4 or IPv6 doesn't always mean that there's a whole different process that your traffic goes through. In the case of ARPs, yes, they redesigned that because they don't want those problems with broadcast storms, but TCP connections, that sort of thing, I believe are all going to be very similar. So now that that's cleared, we'll see the four-way disconnect, and we'll have to wait until the hold time expires. So show BGP summary, pipe refresh 1. So we're still in active state. Show BGP summary, pipe refresh 1. And you can see we're still in established state here because that timer has not expired yet. But I'm surprised there's only one peer. Like, what about the peer to router 2? Oh, we're looking at the wrong router. We're looking at router 1. Yeah, so you can see it's still in. Oh, well, it went into established state. So let's try that again. Oops. Okay, so now we can see this is inactive. Okay, so it went right into active. I think that's something I might need to read more about is BGP hold timers. Yeah, and unfortunately, it looks like oh, no, it did keep running. Okay, good. And now we have a SYN-SYNAC ACK. It looks like we've got the connection collision. So we might have some extra FINACs going through. So we should see like a notification message. Perfect. And in here should be the connection collision resolution. So the one with the higher IP, that's the one that, sorry, not the higher IP, the higher router ID. That's the one that is allowed to initiate the session. So we'll see the router ID being passed in the open message, BGP identifier. So .2 is going to be higher than .1. So we can see the one with the SYN initiated from .2. If we do a follow TCP stream, it's not going to have that notification message in it until, of course, I went and did that, but it's not going to have the collision detection resolution. If we look at the TCP stream with the SYN, the three-way handshake originating on .1, let's find it here. I think this is it. No, that's still on .2. Let's find it. So let's see here, where is it? So this is the one for, so FINAC. So here's, well, let's just do TCP flags SYN. There we go. So now we're only going to get TCP traffic with SYN, and then let's do and IP, whoops, IP.addr equals oh, sorry, IP.source, because we want to look at the one sourcing from the loser of that connection collision resolution, which is the one with the lower BGP identifier, which their identifier is going to be 150.1.1.1. It's going to be an IPv4 address. It's going to be different from the source and destination addresses, but we can assume that the one with the source address .1.1.1 is going to be the one with the route identifier. And we've got to specify in our filter that it's an IPv6 address. So here we go. So here's our found it SYN SYNAC ACK. So, and then there's the FINAC. Here's the, so yeah, we're filtering out everything now, but let's, so here's the first SYN. So let's follow the TCP string on that. And now we'll get that, we'll see, yep, there's that notification message with the connection collision resolution. So the one with the lower BGP identifier, which we can see up here under the open message. What? Wait, I'm confused. Oh, I think we're looking at, yeah. So up here, the one with the lower BGP identifier. So this first open message here. Oh, yeah. So the BGP identifier on this one is 140.1.1, but the BGP identifier of the other message is 150. So this one loses, even though they both end in .2, the first octet of the loser is smaller than the first octet of the winner. Okay, so yeah, I think that's super clear. So now it's just time for the verification steps. We'll see if there's anything interesting in the step-by-step procedure. So here we go, enable the feature to advertise IPv4 routes, IPv4 address into IPv6 sessions. So it looks like you have to have that local address configured in order to advertise IPv4. This actually looks like kind of wrong because you're not, I don't know if you're enabling the feature there. I don't know. It's not worth a download. All right, hopefully these verification commands will all go through smooth and we can kind of keep pace and move on. So yep, the BGP route is established. And it's flapped a few times because I've cleared it out. All right, so let's see the routes that router R1 are advertising through BGP. And you'll notice something kind of interesting. So we're gonna check a IPv6 BGP neighbor, and we're gonna see what routes are being advertised to it. And well, it looks like we've got none, but kind of what I was getting at is during the example, you can see there are IPv4 routes being advertised to that neighbor. So I guess we got to do some troubleshooting and figure out why those routes are not being advertised. So all right, so everything looks good so far. We got our static routes. So then we've got an export policy, perfect, P1, and then P1 is from protocol static, then accept. So I guess I don't understand what the issue is. 140.1.1.1. Yeah, so it's configured exactly as it's configured in the example. Static route, discard, from protocol static, then accept, and it's an export. But you can see there. Oh, okay. I get it. So my neighbor is going to be. Oh, I see. Aha. So it looks like there's a. I think this is actually worth a. No, because it is going to be 140. Let's take a look again. So show int terse pipe match ge dash. So we got 140.1.1.1. So yeah, it's going to have to be in the same subnet. So it is going to be 140. But let's take a look if that's correctly configured. Yes, so it is. I mean, the BGP session was established, so clearly it was going to be. Aha, but here's where the issue is. So, and I think this is worth a downvote because this did cost me some time. So there's no BGP neighbor 150.1.1.2. That's the other side of R2. So clearly you won't be able to see which routes you are advertising to a neighbor that you don't have an adjacency with. So there's no neighbor 150.1.1.2. I show BGP summary. You can see I've only got a neighbor to 140.1.1.2. So let's check the advertising protocols of that. Yep, and everything looks perfect there. Next hop self, AS path I. I am noticing that the AS path is actually less than what they have here. But I mean, did they say 150? I'm confused why there's no. It's only one BGP session to 140, so I don't know why they're talking about 150. I mean, it would make sense that you would have. Oh, let me do a no resolve. Oops. I don't want it to say self for what the next hop is. I want it to show me the actual next hop. So I'm not sure if there's a keyword that will allow that. But if there is, I would like to use that keyword. So like no resolve or something like that. Maybe just detail. So extensive. Nope, I still just get next hop self. So yeah, so unfortunately, next hop self is all I get there. And it looks like my output is a bit different from theirs. But let's submit a downvote and say, let's do this. R2, oh no, we're talking about this one right now. We haven't gotten that far. So R1 has no BGP peer to R2 so R1 has no BGP peer to R2 : 150.1.1.2, only to R2 : 140.1.1 dots, and I don't remember if it was 1 or 2. So let's here show BGP summary .2. Okay, I think that'll be verbose enough. So submit that downvote. Perfect. And move on to the next one. So let's read the meaning first. The IPv4 static route is being advertised to the BGP neighbor R2, router R2. So now let's verify that router R2 receives the IPv4 address that router R1 is advertising to the BGP neighbor over IPv6. All right, so yeah, it's receiving it, and it looks like one of the things they might have done is gotten they just copied and pasted what was down there up here, because we can see that this AS path now matches. I'm not sure if this looks like it's an invalid value for the MED too. I don't think it typically is something like that, and it certainly wouldn't match the AS. So yeah, I'm not sure what's going on up there. Hopefully my downvote was enough for them to look at this part as well. But yeah, a lot of problems with this documentation. So, but everything looks good here. So let's read the meaning. The presence of the static IPv4 route in the router R2's routing table indicates that it is receiving the advertised IPv4 routes from router R1, even though the BGP neighborship is established over IPv6. So yeah, nice and easy. I think we've got one more exercise. Yeah, so we've just got to read this portion here, and then we've got one more exercise, and that's to redistribute IPv4 routes with IPv6 next hop addresses. So stay tuned for that. I will be, I'm gonna keep track of the work I did here. So these are all in separate parts. Here we go, so I already had it kept track of, so I'm gonna cross off what I've done. And then the next one will be, come on, bring me down to it. There we go. So, yep, then we'll read about understanding, yeah, so we'll read about understanding redistribution of IPv4 routes into IPv6 with IPv6 next hop into BGP. Next video, we'll read all about this. Then we'll complete the exercise configuring BGP to redistribute IPv4 routes with IPv6 next hop addresses. And unfortunately, there's not I don't see any, well, I mean, that might be a good thing because it'll be a quicker lab exercise. But yeah, we'll go through and read about that. Just kind of look at what this looks like on the last address. We won't need to move on to layer 2 VPNs because I already did that in another topic. But yeah, so we're just one video away from finishing IP tunneling, and that's the last topic in the BGP implementation section. So we'll be moving on to route policy. Before that, we'll be doing some quick math to see if my rate of pace is appropriate, or if I need to really speed things up, or if I can spend more time kind of elaborating on details. So stay tuned for that. Lots of good stuff to come. Thanks for watching.